my talk will be about offline wallets and how they can leak private keys. In the title I said perfect offline wallets. I will explain soon what I mean by that. First we will start with a little cartoon to get the point of what I'm talking about. So the Bitcoin network, most of you will know how it works. We have like a blockchain that collects all the transactions, and then if Alice wants to send the transaction to Bob, she signs it with her key. So Alice creates the transaction to Bob and broadcasts it to the network. These transactions get collected by the miners and included into the blocks. At one point in time, if Alice's transaction is valid, it will be included into a block that is winning the mining thing, and after that, Bob can see in the blockchain that the transaction happened. That's the basic idea how Bitcoin is supposed to work. We'll see later maybe some problems with that. So, but I wanted to start with that slide to make clear what I was going to talk about. We are going to talk about how Alice is signing the transactions. We are not talking about the blockchain and all the other nice stuff that Bitcoin gave us. We are basically just talking about the transaction itself. So the transaction is created by Alice by performing the following steps. Alice selects a coin that is associated with an address of hers, so it's her coin. She writes a transaction. In the transaction, Bob's address is specified as the receiving address. And then Alice signs the transaction with her private key that belongs to her address. And the important thing here to notice is that the signature scheme used for that in Bitcoin is ECDSA. And our talk will be about some specific properties of ECDSA that we can exploit. Yeah. Next, I want to explain what I mean by offline wallet. So if you want to use Bitcoin, or in the first place it actually looked like this. We had like the wallet software on your PC, but most users also use the same PC for many other tasks like browsing the web, gaming, etc. That means that there can be malware on the PC, and the malware may steal the wallet file. And nowadays the wallet file mostly is encrypted, but then the malware just has to wait until the user uses the password, of course, and the malware can just record the password and send it home. Another setting that you can think about is like an online shop that wants to accept Bitcoin. The easiest way to implement it would be you just have a web server where you run a shop, and the same server runs a Bitcoin client. Here you have the same problem. An attacker can break into the web server, and if he does that, he can steal the wallet file. So basically, these setups look like this. You have like the server and the wallet on the same machine, and that machine is communicating with the outside world. Here the internet, in the case of Bitcoin. So an offline wallet is like the first idea to how to prevent that kind of attacks. So we set up an isolated machine running the Bitcoin client. We do not use the same machine for insecure tasks like running the web server. So it looks basically like this. We have two machines now. One machine is storing the Bitcoins. The other machine is doing, for example, the shop website. And between them, we only transfer the transactions. And the offline wallet is not connected to any other networks. And the server communicates with the internet, giving the service. If your web service is made in a way that you need immediate access to the Bitcoins, you can still have a Bitcoin client on the web server, but you only store a small amount on that. this is what an offline wallet is about. And I want to call this offline wallet perfect if you really make sure that no other information except the transactions is transferred from the wallet to the server. Next slide. Let's say you have very carefully set up such an offline wallet. The wallet is not connected to any network. The wallet software provides transactions to a file. You transfer the file with a CD-ROM, so you really burn the CD, so you make sure that no other information except the transaction will get to the outside world. Does it mean that there is no leak of private information? And the answer is no. And this talk will be about why. So we really can make sure that no other data than the transaction is transferred from the offline wallet to the outside world, but we can still there can still be private information hidden inside the transaction. And at the same time, it can be done in a way that the transaction is indistinguishable from regular transactions. So we use certain cryptographic tools to hide the information. To explain how that exactly works on a technical level, you have to know how ECDSA works, the signature scheme. I will go through it, but maybe not everybody is familiar with the things you need to know for that. But it's not important to get the idea later. So you have an elliptic curve E, a point G on that curve that has a certain order, which we call N, and you have a hash function that you use for doing the signature. And then the user has a private key, which is a number D, and a public key, which is a point on the curve again, which is the point G that we had before multiplied by the number. And then the signature algorithm works as follows. First, the signature program has to pick a random number. This random number is called K. Then from that we compute the point on the curve, which is just the point R, which is the point G we had before multiplied by the number K. And then we perform some more operations. We generate a number R and a number S, and these numbers R and S are the signature. We don't have to go into detail now how this really works. We just have to remember that there's a random number K in the beginning. So the signature can be verified by another party by performing complicated operations. I will not go into detail how that works, but the thing we have to keep in mind is that this number K is chosen randomly, and then we can see that this number has to be secret. If we know the number K, then we can use the formula here in line 4 to compute the private key. So a lot of flaws that have been in the media recently with Bitcoin have come from the fact that this number K was chosen not so random and hackers could guess it. Another problem is if you use the same number K twice, then you can even compute the private key without knowing K, but this is not relevant for this talk. So this means K has to be a good choice. Now we will introduce a new concept that's called kleptograms that was invented by two scientists called Young and Young in 1997 for a different crypto system that is somehow like the grandfather of ECDSA. And I will explain how such a kleptogram works. So the attacker also generates a public and private key pair, the same way like the ECDSA key that the normal user has. And the attacker uses a pseudo random number generator R, and then he can generate two numbers k that can be used in the ECDSA signature scheme, and he generates them the following way. The first one is just chosen randomly, like in the ECDSA scheme we saw before. He just picks a random number k. But he stores this number in memory that will be present when the next signature is created. And then he computes the point R that's used in the ECDSA signature, and all the rest is done like always. But next time, when a signature is generated, the algorithm picks a random bit, 1 or 0, 0 or 1, computes the number Z with a complicated formula. Then it uses a random number generator to compute a second number K2 from that. And as you can see, the number K1 is used in this formula, and then the number K2 is derived from that. And then he outputs the thing and does the same thing again. But this time he uses this number K2 in place of the K of the signature algorithm. So this one is not really a random number, but he is generated with a random number generator, so it's not easy to distinguish. And now the attacker can do the following. So this is the second round we have seen on the last slide. And then now when these two signatures are generated and the attacker sees them, for example with Bitcoin you would see them on the blockchain when the transactions are added, he can do the following computations. You don't have to go into detail how this works, but in the end, from the two signatures he can compute the number K2, which is supposed to be unknown. And as we have seen on the slide before, with knowledge of K2 he can compute the private key. So this is the attack in a technical sense what he's doing, and now we look what that means for the user. Assuming the pseudo-random number generator that he used is really secure, then we know that these transactions, these malicious transactions, are actually indistinguishable from the regular ones. The manipulated wallet does not contain the attacker's private key. The attacker needs to know in advance which curve is used. This is a little small problem with running this attack, because the attacker has to generate his own private key and public key pair. But fortunately for the attacker, in Bitcoin only a single curve is used. And so he just has to generate his private public key pair for this curve. And another property of this attack is only the key that was used for the signatures is leaked through the attack, so other keys are not affected. Only reused keys are vulnerable, but there's two problems with that. Some applications require using the same key. For example, if you are like in WikiLeaks or something, some organization wants to get donations and you put in others on your website, then you will get money at different points in time as donations, and you want to spend them again and again, so you have to do a lot of signatures with the same key. And then there's the problem with HD wallets, which are these types of wallets where you have one root key and all the other keys are derived from that. In that case, if the attacker gets knowledge of the one root key, he can derive all the other private keys as well. So we can now talk about countermeasures to this attack. One countermeasure would be to choose K in a deterministic way. There are several proposals how to do that, but choosing it deterministically doesn't help alone because it is chosen deterministically, but still not known from the outside what value it has, so it cannot be checked whether the wallet is really doing it. So you have to combine it with another cryptographic tool which is called the zero-knowledge proof, where the wallet is proving that it's actually doing the choice of K this way. This countermeasure is not very practical because this type of proofs are very expensive, they require a lot of time. And also this type of proof themselves need a lot of random bits, and the attacker could hide a lot of information inside this proof as well. But at least it has a little advantage. The zero-knowledge proof only has to be checked by the user himself. It's not published in the blockchain like the transaction and the signature itself. The second way to have a countermeasure is to interactively generate random numbers. So this means the wallet doesn't pick the random number itself, but gets the random number from the supervising machine and has to use this random number provided by the supervising machine in a certain way that the supervising machine can see that it actually used it. This is a little bit costly because you need interaction between the supervising machine and the wallet machine. And this setup would look like this. You have the offline wallet and the server, but in between you have the supervising machine, which interacts with the offline wallet to generate the random number and checks that the offline wallet did its job. So now we can go discuss what implications this has for Bitcoin users. You always have to be very careful which wallet software you use, even if you use it on an isolated machine. The fact that you don't connect it to the internet does not mean that no information gets leaked. A malicious wallet implementation can still hide information inside the transaction itself. You should always prefer simple implementations over complicated ones because you can't really check complicated code if it's not doing this. Performance isn't everything. For example, if you look at the Bitcoin Core client, it is using the OpenSSL library. The OpenSSL library is like a big library that was written for everything. It is written in a way that it can perform like millions of signatures in a second if it runs on a web server. But if you are running Bitcoin, you don't really need to create millions of transactions in 1 second. So you can better use a client that uses an implementation of ECDSA that's easier to read, easier to understand, that it's not doing anything bad, because the complicated code of OpenSSL is not very readable.
So basically the Bitcoin Core client, when generating the key pairs, it uses OpenSSL.
Yes.
Okay, that kind of sucks.
Until the next version.
If you need to replace
being replaced. That's a good news. Yeah, microseconds don't matter for transaction creation, so it doesn't matter if you create a transaction if it takes half a second or a thousandth of a second. Yeah, that's it. Are there any more questions? Yeah.
Can you go back to where you started doing the mathematics?
Yes.
Or mathematics, the proofs? Because you, to be honest, you kind of lost me. So take me through this and tell me who is doing what. So I have a wallet, right? And I'm making a private and a public key. So I have a random number generator, I generate a key. And now what's the problem? You're an attacker and you're going to do something. What is it that you're doing?
No, the setup is more, you are a user and you are using the wallet software.
Okay.
But you didn't write the wallet software yourself. You got it from somewhere. The point is that you don't really know what it's doing.
Okay.
You put it on an offline machine and make sure that only transactions...
This is about corrupted wallet software.
Yes.
That's it. Okay.
Yeah,
so
or
now I understand.
Yeah, corrupted wallet software or corrupted random number generator.
Yeah, it doesn't have to be the whole wallet software. If you have like malware on the wallet or a corrupted random number generator, or this attack here.
But that random number generator that is implemented in the software? Or, I mean, your computer also has, as far as I know, random number generation? Or
There are different
okay,
possibilities.
So that's another story.
Would you be able to, I'm sorry, I'm not sure I understand it 100%, but would you be able to, is this resolvable by, so can you just, okay, so, okay, I have to look at this.
The point of this whole attack is that you have to be careful which wallet software you choose, because setting it offline alone is not doing the job of keeping it safe.
Yeah, because somebody can make software that's corrupted and install some
Yeah,
kind
so
of
for-
information track.
Yeah, so for example,
device in it. Okay,
if you
yeah.
install a random binary, that would be hazardous, but if you take the source code, the open source code, and check the SHA checks out for the thing, and then compile it yourself on this air-gapped machine, then you'd probably be a whole lot safer than just trusting this binary.
Or,
And then maybe,
Yes.
Yeah,
or
Let's
just